Imagine a world where there's no lag, no buffering, no data breaches, a world where messages can be intercepted and global collaboration happens in real time, no matter how far apart people are. That's the promise behind the quantum internet. But is it real? Is it close? And what does it even mean to link the world in real time through quantum physics? Let's break it down, not with hype, but with clarity. Chapter 1: Entangling the World. Let's start with the core idea that makes all of this even remotely possible: quantum entanglement. It sounds abstract, but here's the short version. In quantum physics, two particles can become linked so that whatever happens to one instantly affects the other. It doesn't matter how far apart they are. You change one, and the other changes too. Einstein called it spooky action at a distance because it breaks the usual rules of space and time. Now, imagine if we could build an internet based on that. Instead of sending electrical signals or light pulses through cables and satellites, we use pairs of entangled particles. No physical data actually travels between point A and point B in the traditional sense. The information is sort of mirrored, teleported. This concept isn't science fiction, it's been demonstrated. Labs around the world, including in the US, China, and Europe, have already entangled photons across kilometers of fiber optic cables and even via satellites in space. Why does that matter? Because the current internet is fast but not instant. There's always a lag. Even fiber optic cables have limits. Satellites orbit, and that introduces delay. For regular browsing, that's fine. But when you're trying to synchronize a robot surgery happening on opposite sides of the world, or operate a secure drone swarm, or even stabilize global financial systems in real time, those milliseconds matter. Quantum entanglement skips all that. If perfected, this technology would let devices across the planet be perfectly in sync with no traditional transmission time. That's the foundation of a truly real time internet. And it's not just faster, it's also unbreakable. Here's what makes that possible: quantum states can't be cloned. You can't make a perfect copy of an entangled particle without changing it. That means if someone tries to eavesdrop, the system knows. The act of intercepting destroys the data. This gives quantum communication built in security at the physics level. No passwords, no encryption keys, just physics. And this isn't theoretical. In 2020, China achieved satellite based quantum key distribution across more than 1,200 kilometers. The EU has its own quantum internet initiative underway. The US has built a working quantum network between national labs like Fermilab, Argonne, and Caltech. It's still early, but the pieces are moving fast. But of course, entangling a few particles over a controlled lab setup is one thing. Linking the entire world in real time, that's an entirely different beast. There are huge challenges. Distance is one. Entangled particles degrade over space. Maintaining their fragile states across long distances isn't easy. There's also the issue of infrastructure. Our current internet isn't built to support quantum transmission. We need quantum repeaters, quantum routers, new satellites, new fiber lines. That's a full system rebuild. And yet, the incentives are massive. Governments want it for security, banks want it for stability, scientists want it for instant collaboration, tech giants want it to break the cloud open. And at the center of all of it is this bizarre, counterintuitive idea from quantum mechanics that you can link two things without sending anything between them. It's like teleportation, but for information. So now that you understand the principle, the next question is, how do we make it real? And how far away are we from it actually being usable outside of labs and test beds? Let's talk about the infrastructure behind this invisible web. Chapter 2: Building the Invisible Web. To make a quantum internet real, we need to rethink everything, not just the cables, but how information moves entirely. The internet today runs on routers, servers, and undersea cables. But quantum information doesn't travel the same way. You can't just copy it and forward it like an email. Quantum data is fragile. The moment you measure it, you risk destroying it. So, to move quantum data across long distances, we need new tools. One of the most important is the quantum repeater. It works kind of like a relay station, except instead of amplifying a signal, it preserves entanglement between distant points. The problem? These devices are still in the early stages. They require ultra cold temperatures, complex hardware, and are far from plug and play. But researchers are pushing fast. Several teams have demonstrated basic quantum repeaters over fiber networks, sometimes using atoms trapped in crystals or photons bouncing through special quantum memories. The challenge is scaling it up. To link cities, countries, continents, you need thousands of these repeaters and they all have to stay in sync. That's a precision problem we've never solved before at this scale. Then there is the issue of standardization. Different labs and countries are experimenting with different materials and methods photons, ions, diamond qubits, superconducting circuits. But there's no single protocol everyone agrees on yet. Think of it like trying to build a global railway system, but no one's agreed whether the tracks should be narrow gauge or standard gauge. That slows everything down. Satellites are one way to get around this. In 2017, China launched Mischievous, the first satellite dedicated to quantum communication. It used entangled photons beamed between orbit and ground stations to demonstrate secure communication over thousands of kilometers. This bypasses some of the problems on Earth, like fiber signal loss, but comes with its own challenges atmospheric interference, tracking precision, and limited bandwidth. Still, the results were stunning. It proved you could create a space-based backbone for quantum networks. That's now part of several national strategies. The European Union has its EuroQCI project. The US has the Quantum Internet Blueprint from the Department of Energy. Singapore, Japan, Canada, they're all building small-scale testbeds. Everyone wants in. What's interesting is how this isn't being driven purely by governments. Private companies are jumping in too. Amazon has launched quantum key distribution satellites. IBM is working on quantum safe cloud infrastructure. Startups are building quantum routers and even quantum as a service platforms. It's not just a research project anymore. It's becoming an industry, but it's also becoming a race. And that's where things get geopolitical, because whoever builds this first will control the next layer of global infrastructure. Just like whoever built the first undersea cables controlled communication. Just like whoever built the GPS system controls navigation. And it's not just about speed or security, it's about who sets the rules. That's why you'll see nations trying to secure quantum corridors, secure entangled routes between key locations. That's why the US Japan South Korea alliance on quantum tech matters. That's why China is laying fiber between cities that are part of its Belt and Road Initiative, not just for regular internet, but for quantum grade networks. We're watching the blueprint of the next internet being drawn, not in public, but behind the scenes by physicists, engineers, and national security strategists. It's not here yet, but the tracks are being laid. And if this invisible web becomes reality, it's not just going to change how we connect, it's going to change who connects and who controls it. In the next chapter, let's look at what the quantum internet could actually do. Beyond speed and security, let's explore the real world applications that make this so much bigger than just better Wi Fi. Chapter 3 Beyond Speed, What the Quantum Internet Can Do. Most people think the quantum internet is just a faster internet. It's not. It's a different internet. Yes, it can offer unbreakable encryption and real-time sync, but its real power lies in what it enables. It creates possibilities that the classical internet can't touch. Think of it less as an upgrade and more like a new layer sitting beside the one we already have. Start with distributed quantum computing. Right now, quantum computers are rare and expensive. You can't exactly keep one in your house, but with a quantum internet, multiple quantum machines across the world could be linked, sharing entangled states and working as a single system. That could massively increase computing power for simulations, drug discovery, material science, and more. It would allow quantum cloud services that are actually quantum, not just classical servers running quantum simulations, but real time access to entangled qubits over distance. That's a leap. Then there's clock synchronization. Sounds boring, right? But it's one of the most important technical challenges today. GPS, financial transactions, energy grids all depend on ultra precise timekeeping. Quantum entanglement can sync atomic clocks across continents to levels of precision that no current system can match. That means more stable financial systems, global markets running in perfect time, no drift, no delay. There's also quantum sensor networks. Imagine an earthquake early warning system where the sensors are entangled so they detect shifts at the exact same moment across a region, or a telescope made of entangled sensors spread across the planet, creating resolution sharp enough to image a black hole in real time. This isn't science fiction. We've already used quantum principles to take the first picture of a black hole. A quantum network just pushes that further. Then there's national security. If your communications can't be intercepted, even in theory, that changes diplomacy, defense, and intelligence completely. It redefines trust at the infrastructure level. You're not securing messages with software, you're securing them with physics. And yes, it'll affect everyday people too, not directly through browsers or apps, at least not at first, but through the services built on top of this network. Banks, hospitals, governments, and supply chains using quantum secured connections to protect your data, transactions, and records. The early days of the internet weren't personal either. It took time, but it spread fast. And this could be even bigger because the stakes are global right from the start. We should be clear, a full scale global quantum internet is still years away, maybe a decade, maybe two, but regional networks, national testbeds, city to city quantum links, those are already here. What comes next is integration. That means bridging quantum and classical systems. It means new hardware, new protocols, and training an entire new workforce to handle a network that behaves nothing like the one we are used to. It also means governance. Who owns this infrastructure? Who controls access? Who defines the standards? Because if the quantum internet is going to link the world in real time, then it matters who gets linked and who gets left out. We are standing at the edge of a new internet, not just faster, but fundamentally different. One built not on wires and code, but on entanglement and uncertainty. And what we build on top of it could reshape everything from science to security, economy to identity. So the next time someone says quantum internet, don't just think speed, think possibility. Thanks for watching. Check out the references in the description to explore further.